Hello, welcome back to the third lecture of week 2. So in this lecture, we'll continue learning about recursive algorithms complexity, and finally, we'll get to talk about the time complexity of merge sort. Okay, let's get started.
We used the two examples last time and concluded these two types of recurrence relations and their corresponding time complexities. I also asked you to analyze the complexity of recursive binary search. So now let's look at it together. Here is a recursive binary search algorithm. The list A is sorted and we are searching for value V. Note that the binary search only works for sorted lists. If a list is randomized, we need to use a linear search. The idea of binary search is to compare the target value V with the middle item of A. If there is a match, we can return the middle index. Otherwise, if V is greater than the middle item, we continue the search only on the second half of list A. On the other hand, if V is smaller than the middle item, we continue the search only on the first half of list A. In each iteration, we can reduce the number of items to be searched by half. This is also how this algorithm gets the name binary search. It should be straightforward now for us to figure out the recurrence relation for binary search. The base case is when the list has only one item, then T1 takes a constant running time C1. If n is greater than 1, the running time of searching for n items would be some constant time C2 spent on making comparisons and some other sequential instructions, plus the running time of binary search with only half of n. Now this is clear to us. Let's derive the closed form of Tn using substitution. So we know Tn is C2 plus Tn over 2. Now we can replace this. That'll give us C2 plus C2 plus Tn over 4. And then we can replace this. So that'll give us C2 plus C2 plus C2 plus Tn over 8. Right? Keep dividing by 2. And then we replace this. That'll give us C2 plus C2 plus C2 plus C2 plus Tn over 16. Okay, so we'll keep going on. In the end, we know we'll have a bunch of C2s. And then we'll get to the base case, C1. Now, the form looks quite straightforward. We just need to figure out how many C2s. Okay, so let's check the pattern. So here, when we have 2, there is 1 C2. When we have 4, there are 2 C2s. When we have 8 here, we have 3 C2s. When we have 16 here, we have 4 C2s. So when we get to T1, so that's essentially n over n, by observing the pattern, we know 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, 2 to the power of 4 is 16. So 2 to the power of log 2n will give us n. So we know we have log 2 n C2. Final form would be C2 log 2n plus constant C1. And we know this function, the complexity of recursive binary search is in log n. Now we have seen 3 different recurrence relations and their corresponding complexities. Note that these recurrence relations can be used to characterize many recursive functions. Here is a graph comparison of different orders of growth. We know n is linear. Log n has a much slower growth rate, so log n algorithms are generally considered as very efficient. the running time of n-squared algorithms increase really fast, especially comparing to n. When we have an exponential complexity, say 2 to the power of n, its growth rate is just astonishing. Even small values of n can yield very, very high running time. Finally, we're ready for merge sort. It should be easy for us to write its recurrence relation now. When the input size is 1, that's the base case, merge sort takes a constant time C1. When n is greater than 1, constant C2 covers sequential instructions such as computing the middle index. Then we have the merge function, which we showed in the previous lecture, is in theta n. So we can use C3 times n to denote its complexity. Last, we have two recursive calls of merge sort with input half of the original size, n over 2. Okay, all seems good. Now let's compute the closed form of Tn using substitution. Tn is C2 plus C3 times n plus 2 Tn over 2. Let's replace this. All right, and then we can rearrange this. Okay, now we can replace Tn over 4. Just go a little bit further to be able to see the pattern. All right, so we have C2 plus C3 n over 4 plus 2 T n over 8. So we can rearrange this. 1 plus 2 plus 4. We have C3 n plus n plus n. And then we have 8 Tn over 8. Okay, now we can write it one more time. Replace Tn over 8. C2 plus C3 n over 8 plus 2T n over 16. Rearrange it. So we have C2 1 plus 2 plus 4 plus 8. And we have 1n, 2n, 3n, 4n. And then we have 16 Tn over 16. Okay, so now eventually we will get to, now we know the form, eventually we'll get to C2, 1 plus 2 plus 4 plus 8. We'll stop at some point. We'll decide what the last number is. And then we have C3, we have a bunch of n's. We'll know how many n's we have. How many? And we have n times t n over n. And then we know that's a constant, C1. So now we just need to figure out how many n's we have, and then what's the last term. So now let's find the pattern. So when we have 2 here, we have 1 n. When we have 4 here, we have 2 n's. When we have 8 here, we have 3 n's. When we have 16 here, we have 4 n's. So we have this power of 2 relationship. So it should be easy for us to figure out. We'll have log 2 n, this many n here. And then what about when we have 2 here, we have 1. When we have 4 here, the last term is 2. When we have 8 here, the last term is 4. When we have 16 here, the last term is 8. So the last term is n over 2. So what's this? Now we need to figure out what's 1 plus 2 plus 4 plus 8 plus n over 2. So we know all these numbers, they are powers of 2's. So we can write it as 2 to the power of 0, 2 to the power of 1, 2, 3, Let's say the last one is 2 to the power of k. Okay, and then we know 2 to the power of k would be n over 2. We'll deal with that later. So what's this? You may know the answer already, but for some of you that this does not look very straightforward, I have a quick way to figure this out. Let's say if this is x, so what is 2 times x? That'll give us 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 4, and then the last term would be 2 to the power of k plus 1. All right, and what happens if we subtract these two? 2x minus x. So that'll get rid of this term for us. Right, so we know what's left would be 2 to the power of k plus 1 minus 2 to the power of 0. Now it should be really clear. So we know x would be 2 to the power of k plus 1 minus 1. So our answer is this whole term here. We have the answer that's 2 to the power of k plus 1 minus 1. So what is k? We know 2 to the power of k is n over 2. So k would be log 2 n over 2. And then x would be 2 to the power of log 2 n over 2 plus 1 minus 1. And then we'll get 2 to the power of log 2 n over 2 times 2 minus 1. And then we know what this is. That's n over 2 times 2 minus 1. So we get n minus 1. So this whole thing, x here is n minus 1. So now we know in the final term we have n minus 1 times c2 plus log 2n times n times c3 plus c1. And now we know the highest order term would be n times log 2n. So the complexity of merge sort is in theta n log n. Now we can add the final row to our table of patterns. Note that the base cases do not have to be n equals 0 or n equals 1. In fact, any specific small number would be okay. When the input size is a specific value rather than growing arbitrarily large, the running time should still be a constant. There are infinitely many possible recurrence relations, but these four will cover the vast majority of recursive functions that you will encounter in the real world. Okay, that'll be all for this week. There was a bit of math involved. However, the rule of how substitution works is quite straightforward, so you just need some practice. You should be able to analyze a recursive function and derive its recurrence relation. If the recurrence relation is one of these four, or very similar to these four, you should be able to state the theta or big O complexity of that algorithm. Next week, we'll continue with complexity, but instead of discussing the complexity of an algorithm, we're going to talk about the complexity of problems. I will see you next week.